And whenever you are ready for that, please give me a note.
So we have 1 minute left for start.
Yeah, sure. Just take your time.
I had started the recording and online also. They typed that.
Yeah. And whenever you are ready for that, please give me a note.
Yeah. So we have 1 minute left for start.
Yeah, sure. Just take your time. It's interesting that there is almost 20 minutes, oh, sorry, 20-second delay when I'm hearing, when I spoke and when I'm hearing back my sound. It's unbelievable.
Maybe, I don't know. And no, on YouTube, it takes time actually. There is a delay of 10 seconds in the.
It's okay. I mean, it's a huge network, obviously, and this is okay. We had already 3 minutes delays earlier.
Yeah, so you can start, Professor.
Excellent.
Yeah, you can start.
I'm starting then. The second lecture today will be about massive data management and analysis. Please, it is not exactly the same as big data management, although there is an overlap between the two things, which I will emphasize in my presentation. So this is also decomposed into 2 blocks. And in the first one, I will talk about the underpinning trends and concept of massive data and massive data processing. In the second one, I will visit the issue of using blockchains within cyber-physical systems environment. The first thing what I would like to mention is the change of the data sources and type over the time. So actually, if we start out from the so-called handcrafting age, when know-how and familiarity was the form of knowledge, then we just had the human memory to store it. Later in the machine age, technical drawings came up, and then they could store, in addition, in written form, various company data. Then in the recent information age, actually databases and information systems are handling our data. And we definitely go towards a massive data age when the internet and cloud provide facilities for even larger scale information system data management and even smart data management. So definitely what was found in the field of big data processing, increase data volume, variety, and complexity, it also will have impact on the massive data management inside our physical systems. So if we consider the worldwide data shipment by various media, which I received from a official source. So actually you can see how the hard disk, the solid state disk, the non-volatile memory, different forms of the non-volatile memory. Please switch off the microphone because I'm hearing noise. Thank you. Optic disk or tapes taking part. So as you see, surprise that the tape-based archiving is still there, even in 2025, according to this prognosis. But what is interesting that the hard disk drive share and the solid state drive share are also increasing, or both are increasing, while the non-volatile thing is just remains as they were a couple of years ago. So if you see or look into the storing massive data, then we can see also a change here, which are described by these different curves. So the enterprise related data in terms of its percentage, it is not increasing. What is decreasing, for instance, the directly consumer related data, but on the other hand, the data which are stored on public clouds are almost with the same pace increasing. Then the creation and storing massive data are also interesting because actually the major source of this type of data is the edge. And then you can see that what data and what percentage of data is forecasted to be created by the endpoint devices and how much will be stored by the endpoint devices, what will be created on the edge and what is stored on the edge, and what is related on the what is created on the core of cloud system services, and what is stored there. So first of all, the edge store will not increase, and the edge creation will not increase significantly. The endpoint store will radically decline, while the generation of the data there remains significant. And then what I didn't mention, the data which is stored on the cloud, this will increase, but the cloud-based data generation will be permanent. So these will be influential trends for the cyber physical system development as well, and obviously the cyber physical systems will contribute to these modes of generation and storage. What we are going towards is actually the so-called global data sphere. And the digital communication assumes that everything can be characterized by and can generate data, and this is the very reason of going to the global data sphere. The data is an intangible asset and underpins most intangible assets like patent and goodwill as well. The global data sphere is a content universe of all data that is captured, created, and replicated. That was the reason why I started with these figures at the beginning, because they show how the things are coming together and complementing each other. The global data sphere is increased in any given year across the globe with a wide variety of contents, and it is based on the key interdependencies between the core, the edge, and the endpoints. I gave an example for that. So in the process of implementing this global data sphere, and obviously it is also developing naturally, so in a sense it is a social technical system. Different typical sources of and social sources of massive data should be identified. So we can talk about a socialized segment of the global data sphere, which includes non-entertainment imaging data, medical imaging, surveillance imaging, geographical imaging, includes entertainment media data like digital TV, radio, video games, movies, selfie, advertisement, also includes productivity data, like apps outputs, PC data, technical documentation, publication, includes communication data, mobile phone, video conference recording, chat, voice on internet protocol, and so on and so on. And then it also includes commercial data, for instance, RTM data, fuel pumps data, just an example, insurances data, shop purchases data, parking data, and so on and so on. So it is a huge variety of data, and it is aggregative indeed. So the yearly increase of the global data space is enormous. So this particular source, what I referred to several times, forecast that somewhere before 2025, we reach the 175 zettabyte. I tell you frankly, I cannot imagine what it means. For me, a million is already a far value, billion, but a zettabyte is really a kind of question for me. So the motivations for the data science to follow these processes can be summarized in the following. So data science is interested really to reveal the underlying mechanisms of big data and massive data, turn data into knowledge, understanding, and wisdom, gain insight from big data, convert big data into business value, enable data-driven decision-making, facilitate data-driven decision support, implement and combine data products, services, cultivate and maintain big data ecosystems, enable data-intensive scientific discovery, and also to redefine data-centric next-generation CPS functionality and architecture. So quite a broad activity profile. Luckily, also cyber-physical systems are involved. Then a very brief comparison is presented on the next table, what I already have called out, because the basic resources where we store data are the data pools, or often called data lakes, then the data warehouses and the databases. The database concept is well known. The data warehouse is proliferating right now, and the data pool, which is a much looser formation construct and much less deterministically manageable, is just proliferating at this very moment. Please read the differences. The time is running. I have to go further with other things. So the major issues for the big data research is to embed or to cover the big data representation issues, to find solutions to represent big data repositories according to heterogeneous formats and over different memory support, big data management, solutions for access pruning, indexing, fusion, querying, visualization, archiving, context capturing, and so on and so on. Then big data processing tools and methods for qualitative and quantitative data transformation, exploration, and validation. And then big data intelligence, which means semantic transformation, AI application, inferring, reasoning, and knowledge warehouse. What we can say is that new kind of more comprehensive, objective, and predictive knowledge is expected. Just consider, for instance, our smart cyber-physical systems, which will not be able to make reasonable and reliable decisions based on loosely formatted knowledge. So, having mentioned this, we also can pay attention to those sort of sets of data operations, data manipulation activities, what are needed or what are related to smart cyber physical systems. if we start out from the real world, which is the source of information, the message, data, then we are talking about a datafication activity, which means that we want to capture everything in terms of data. You remember at the very beginning, I mentioned that the conventional definition of cyber physical systems, that they are software integrated systems, are to be changed. Here is the explanation that the data is playing such an important, crucial role that really we have to consider data as integrator of cyber physical systems as well. So the datafication is followed up by the so-called data wrangling or mundane technologies, and then if it is happened, so there is some sort of clearness, then sort of reliability achieved with the data, then they can be subject of data analysis. And then obviously the data analysis helps us when it happens in the cyber physical system to have a better data understanding, and also it is fed back to the datafication issue, because based on this knowledge, based on the understanding, we can improve our methods. But it also leads to a kind of opportunity of automated decision making. On the other side, data analysis is also providing data insight, sometimes visual, but more important is the semantic insight. And then it means that the visualization, storytelling, and communication of data produces opportunity for more intensive decision support. And then obviously the data insights also available, also make capable us to produce data products with cyber physical systems, something like the DevOps in a more general big data processing. And this is how we get back to the real world and the data situation. So these are the most general operations what we have to consider with respect to a smart cyber physical system. But it is also important here to see that there are various platform-based data management approaches. For instance, this scheme, layered scheme, has been published a couple of years ago, and it says that the basis of platform-based data management is wireless sensor networks. And then the whole procedure goes through from real-time data sensing, real-time data capture, real-time data streaming, and preliminary data analysis and data processing, the concrete processing, and then the data which processed according to this framework concept goes to storage, and then data access and retrieval, data visualization, statistical evaluation, knowledge synthesis, and finally knowledge verification activities are completed. So this is the essence of the data management platform, and on the other side we have the data analytics platform, and there are connected through data storage, as you can see. There are proposals to use similar abstract platform concept for actor management as in the context of cyber physical system. Here the input is the data storage and data access and retrieval, computing control data, validation of control data, transmitting control data, and control of actuator devices are considered, and this is how we get to the concrete physical actuators and actors. So this is how everything becomes connected, and a closed loop is formed through the physical subsystem. So this formation is often referred to as actor management platform in the literature. We don't have to forget that cyber physical systems will have various actors, for instance, based on the smartness, they can be intelligent agent, informed agent, or ordinary agent, and that actor management should consider that, and based on the cooperation that can be autonomous or can be collaborative or even swarm type of agent, and it has all requirements and demands for the concrete implementation of an actor management platform. So the other issue is the data routing, because cloud providers are contenders for enterprise data storage and services. They work according to the following servicing scenario. The data are collected at the input endpoint, and then data travels the core, the edge, and the endpoints, and the data are pre-processed and processed at the edge. The data are propagated and stored at the core, and data are retrieved and distributed backward, and the data are distributed to the output and nodes. This routing is unfavorable overhead and very complicated to implement in the real life based on the cloud, and this is why more attention is given to the implementation of this routing on the edge. The next thing is the data wrangling topic, which I would like to elaborate. Again, there is an animation error here. I don't know why, sorry for that. But I mentioned that datafication refers to recording real world into information, and this way represented the real world as data. So data science projects need to perform a series of pre-processing activities on raw data, including data audit, data cleaning, data exposition, data integration, data reduction, and data labeling. Data wrangling, or often called the data mingling, is one of the novel terms for these sort of curing and consolidating activities of data science. Data wrangling is employed to turn messy data into tidy data and includes a series of data processing activities, for instance, enhancing data quality, reducing complexity of data computing, and improving the accuracy of data processing. It is important for us to know that data wrangling highlights value-added processes through integrating the clarity, design, critical thinking, and curiosity of data scientists into data processing. Important issue for cyber physical system is processing time series and its components. Many of you most probably know very well that time series is a set of regular time ordered values of quantity obtained at successive times, often with equal intervals between them. Actually, time series data is one of the constituents of the message data which is processed by cyber physical system. That's why I would like to elaborate a little bit. So time series data typically show 4 major patterns: the trend, the seasonality, the cyclic variation, and the random or irregular movement due to short-term unsystematic noise or error. Time series data may be time-stamped or without that. It is easier to process time-stamped data inside the physical system, but it needs more effort and computational capacity. Features help conditioning and inferring time series signals. So this is why the feature concept is also extensively used in the time series processing. Here are something which is a visual illustration of those sort of four major patterns that you can see in time series data whenever you work with them in the data enabled side of the physical system. So this is, for instance, a original time series, a features time series, and then this is the trend. This is the seasonality. This is the cyclic variation. C is this periodic character, and this is the random movement, as I mentioned. So this is how a time series is decomposed into more semantically self-speaking signals and that can be used for reasoning or other purposes. The major characteristics of time series data are that they have a natural temporal ordering, and this can be used in reasoning with time series data. Each time unit can capture only one data value. A data at some time is statistically serially dependent on preceding data of the same time series. There might be autocorrelation applied, and it can be used to refer to the degree of similarity between the values of the same variable over successive intervals, time intervals. And the main data mining tasks related to temporal data are forecasting time series based on historical data, recognizing time series patterns, detecting anomalies, transients, and onset of signals, and classifying time series based on their behavior over time. Again, a animation issue here. I would have called your kind attention to the fact that in the practice and also in our practice, Kalman filters are often used for dealing with time series data, completing time series data, and pre-processing these sort of data. So actually, it is a regulative protocol. The system provide output data. Obviously, there might be certain set of output data missing, not obtained from the system, which otherwise would be needed for the reasoning. And then it is put into a mathematical model, and the mathematical model provides output data, the so-called computed output data, which are brought together with the available, let's say, system-produced or measured output data, and this is the transfer to the Kalman filter. The Kalman filter obviously may change the mathematical model, and this way actually defines a kind of error level and tries to reduce the error level. This error is always interpreted as a difference between the available output data and the computed output data. This is what the Kalman filter can make a decision based on. Because we are almost at the end of this book again, let me offer some literature to further study. For instance, Eckhoff's famous paper From Data to Wisdom. It's a bit old, but still a kind of rotating paper. Then Gordigan and Zon's paper on data science trends, perspective and prospect. Jordan and Mitchell paper on machine learning trends, perspective and prospect. Reader and Simon paper on big data, new empiricism and its epistemic and socio-political consequences. Then Who and You edited a book which was published by Springer, and I found it very informative, the big data analytics for cyber physical systems. And then other edited book, Dorman, Song and Snag, Big Data Analytics for Cyber Physical System, Machine Learning for the Internet of Things. Thank you very much. This concludes this first part of the presentation. So I go back and stop sharing the screen, and I would like to see if there is any comment, question related to what I mentioned.
So participants, any questions?
No, sir, I don't have any questions. Thank you, sir.
No. So it seems there is no question, Professor. So
Thank you.
we can continue with the next.
Sure, then we can go further, I believe, and then sorry, I start sharing the screen again, and we are going on with computing, I believe, or recording, sorry. Yes?
Yeah, it is on.
Sure, then let me go into the second block, which is about the concept, architecture, elements, and workflow of blockchain. Actually, the blockchain technology has been recognized very recently as a potential future means for cyber physical systems. There are research efforts, ongoing research efforts in our days, but it is about just exploration of the opportunity rather than providing some robust and widely accepted technology dedicated to cyber physical systems. I don't know how many colleagues are dealing with blockchain application in manufacturing context. Most probably some of you are busy with it, but let me give you a kind of introductory overview, and then I would like to broadcast a movie in which excellently every major issue of the fundamentals of blockchain and blockchain technology is presented. So in general sense, blockchain technology is seen as the next computational paradigm shift in the information industry. It has been popularized as a foundation and encryption platform for cryptocurrencies such as Bitcoin. This can be used in cyber physical systems as a secure technology for data handling and managing digital transaction reports. Blockchain is a set of distributed databases in the context, or this is what blockchain can deliver for cyber physical system, namely distributed databases which are known in the original concept as block that contains records of digital transactions. Interconnected blocks support the decentralization of systems. And on the other hand, blockchain ensures that data are securely distributed and publicly visible by the stakeholders of a CPS or whatever other system that will be mentioned soon. Many researchers refer to BC as a publicly distributed ledger, which means a book of record used to sort and summarize transactions. So now let's try to understand the main concept based on a very useful movie. I leave my presentation. I start this movie. It's and maybe you can see.
Professor, the sound is not very clear. Professor Emre,
Yes, please.
yeah, the sound is not coming very clear actually.
Oh. In that case, I have to stop with it. Can you hear me well?
Yeah, I can hear you well, but
Oh, sorry, then I have to continue with the presentation because at this very moment I don't have opportunity for changing the decoding of the sound. I could do it, but anyway, I can provide the link to this video and everybody can see
yeah,
it again.
right.
Sorry for that. I didn't know that we have this problem. Maybe it is a bandwidth problem for the time being. So there are two things what the gentleman would explain in the part, the smart contracts, which are important elements of the second generation blockchain implementation, and then also about the application of opportunities. But now I come back then to my presentation material and continue with the written stuff what is here. So the ingredients of the blockchain is the first thing then what we have to see as a connection to this video. And the major ingredients are, for instance, the users who are anonymous. Then the transaction transparency is a concept with blockchain that deals with. Then the e-cash schemes is the third one. The fourth one is the consensus mechanism between multi-parties. Then smart laws and contacts also. And the hash cash, you have seen, at least if you didn't hear it, that hash codes are playing an important role in the implementation. So these are the ingredients. And in addition, there are enablers, for instance, state machine replication, peer-to-peer network, then open source programs, digital wallet software, for instance. It's also related to the Bitcoin, and the Ethereum platform are the most important enablers. So let me introduce now the primary type of blockchains, which can be public blockchains, open to public nodes. Anybody can be involved in the decision-making process using a distributed consensus mechanism, maintaining a copy of the ledger on their local nodes, but nobody has ownership of the ledger. We can talk about private blockchains, which are not open to the public, but to only a group of people or organization, and the ledger is shared to its participated members only. And then we can talk about a semi-private blockchain, which which means that some part of the blockchain is private and controlled by the group or organization, and the rest is open to the public for anyone to participate. There is a specific flow of information. You will see a complex meandering figure here, which describes the flow of information processing. The first element is the transaction initiated by the user. The second one is that the transaction becomes represented online as a block. The third step in the flow of information processing is the hash generation, and as you heard, a hash is taken over from the last block for the actual block in order to connect to that. Then a nonce is generated. The nonce is a kind of unique identifier which can only once used by any system. And when it is generated, then with the hash and the nonce, the block of the transaction is uniquely identified, and then you can get these sort of identification codes. Then the block is broadcasted to every node of the network, and then all nodes of the network are requested to approve the transaction as well. The process is that if it is not done. Then when everybody agrees on the genuinity of that particular block, then the block is added to the chain of the block, the existing chain of the block, and the blockchain provides then a transparent record of the transaction. And the transaction is executed then on the network. So this is the process, rather complicated, not so easy to implement without failures, but actually there are already open programs which can be used for certain development. Important for us to hear about the decentralized and layered structure of the blockchain. And actually, this decentralized structure makes it a kind of tamper-proof technology. So BC implements a peer-to-peer network that runs on top of the internet. And there is an architecture in which it is managed, and this architecture is divided into layers as it is normally with the modern architectures. And these three layers are the application, the decentralized layer, and the peer-to-peer network layer. The application layer contains the application software of the blockchain, and it also provides a human-readable application interface on top of blockchain. So it means that through the interface, the users can keep track of their transaction. For instance, if you go back to the cryptocurrency domain, then the Bitcoin wallet software creates and stores private and public keys, enabling the users to keep control over the unspent Bitcoins. This software can be installed anyway on any computer or mobile devices and also can be hosted on third-party platforms. So then let's diagram the architectural elements of the blockchain, and let's see what they include on a lower level. The peer-to-peer network is the lowest level, and then the decentralized ledger is connected to that, and the highest level is the applications layer. There are two constituent elements in the peer-to-peer network layer. The node types are handled and the messages. The decentralized ledger is much more densely populated with computational concepts, the core discipline identification and recording and management, the tokenization, transaction management, block structure handling, proof of work, as we have seen in the introductory video, the validation, the consensus mitigation, blockchain generation, and mining of information are all related to this decentralized ledger. And then the application, one application what I was referring to, the wallet, for instance, in favor of the Bitcoin. So this is how the blockchain is architectured, and this is how we can import it to the conceptualization side of the ecosystem. So something about the realizations and usages of blockchain now. Based on what you heard so far, it is obvious that the blockchain lends itself to advanced information chain management by promoting transparency and traceability in transactions. A paper what I later on will suggest you from Swan identified three realization forms of blockchain. The blockchain 1, which is related to handled cash, transfer of currency, remittances, and payment systems. The blockchain 2, which is related to establishment of smart contracts, make extensive transactions in various financial economic applications, stocks, bonds, loans, and mortgages. And blockchain 3, which refers to highly scalable and adaptable application. Actually, it is more about forwarding the initial blockchain concept to even engineering and medical applications, like in the I wrote here the fields industry, science, culture, and even art. So, based on the literature, we can say that blockchain technology has begun to make deep economic, political, legal, and humanitarian impacts, and for this reason, it is wise to consider it, and especially the advantages for cyber-physical system development. Let's see now what these so-called generations of blockchain means. The blockchain one began originally as the deployment of cryptocurrencies in applications related to cash. The term Bitcoin and blockchain are often used to refer to the same thing because Bitcoin simultaneously represented three different things. Bitcoin can be understood as the underlying blockchain platform. Bitcoin can refer to the protocol that runs on top of the blockchain platform. And if Bitcoin also means the digital currency itself, which was actually the first cryptocurrency created. So these three layers of Bitcoin are general structure for modern cryptocurrencies, which are layered or certified as blockchain protocol and the currency. So the last thing what I want to mention about blockchain 1.0 is that it encompasses the computational mechanism of the Bitcoin currency. Different additions have been introduced in the blockchain 2, which is the next big tier in the development of the blockchain industry. There are many different categories and consideration of blockchain 2.0, but the definition and the standards are not out there yet, so not everything is shared at this very moment. And while the blockchain 1 is for the transfer of cryptocurrencies, blockchain 2 is for transfer of assets beyond currency from the creation of the unit value. And this is why we can consider even information structure exchange and confidential company knowledge exchange in the framework of cyber-physical system. Much of what is transferred on blockchain is controlled by so-called smart contracts, maintaining ownership and access rights. The most prominent realization of blockchain is the Ethereum, and it was introduced, or it has introduced the concept of smart contracts or decentralized autonomous organizations. This resource leads to the decentralization of the transaction-based system, such as a family of cyber-physical systems which intends to provide these type of services, informational services. Blockchain is operationalized based on the smart, blockchain 2.0 is operationalized based on smart contracts, and this has become a leading topic of discussion and research in the context of realization of blockchain. Essentially, smart contracts are autonomous programs that are routinely executed when predefined conditions are met. The great advantage of smart contracts in blockchain 2.0 is that they are impossible to hack. Thereby, they reduce the cost of verifications, arbitrations, and fraud. In the same way as blockchain 1.0 solved the double spend problem, blockchain 2.0 is expected to solve the so-called moral hazard problem that is common in the financial market. Here is a table in which I try to compare the blockchain characteristics for the 1.0 version and the 2.0 version, and also to identify some benefits, for instance, that with regards to blockchain 2, it is a benefit that it is not logged into one vendor or can leave a more complex request and can partition information to suit needs. And then it also solves privacy and regulatory requirements and overcomes speed issues and computational cost and can tailor solutions around operational needs. The last thing what I would like to mention here is actually a outlook into the future, because blockchain 3, although identified as the forthcoming version of blockchain theory, but it is not yet fully developed and implemented. Nevertheless, as been demonstrated by the Ethereum and Bitcoin platforms, the blockchain technology encourages automated resource allocation for intangible or tangible assets. It also facilitates interaction between the humans and machines. These are the two focus areas where blockchain 3.0 is targeted. Obviously, a long way to go there, and it is just cultivated in the research laboratories, because what is used in the industry at this very moment is blockchain 2.0, and the majority of applications are based on that. Blockchain 3.0 version is expected to improve the capabilities of various platforms while overcoming their observed limitations. As I try to indicate above, blockchain 3 is mostly a theoretical concept. Even the methodology development is lacking behind and hasn't been adopted in the global informational infrastructure yet. The diffusion of this sort of technology, nevertheless, is expected in identification, justice, art, education. In the end, we can talk about different other additional types of blockchain which are making our life complex. And with a view to the fact that the time is almost elapsed, I would like to go to the suggested literature issue and to mention a couple of seminal and meaningful work. For instance, I referred to this particular book earlier, Swan compilation on blockchain, a blueprint for the new economy, is really reading. The Piero, what is the blockchain? It is a recent overview of the fundamental concept and the evolution. And Crosby and the other authors wrote a paper on blockchain technology beyond the Bitcoin, typically focusing on the smart protocols. Zaro and his co-authors wrote a paper on blockchain-enabled cyber-physical systems, and they reviewed the recent development. Deveroglu and the co-authors wrote a conference paper with the title Journey in Applying Blockchain in Cyber-Physical Systems. And the last one is great, and the co-author's paper, the blockchain and cyber-physical systems. So thank you so much. I have to stop here, and I would like to remind you that the first block was about massive data management in next generation cyber-physical system. It emphasized the importance of dealing with time series data and their value improvement. The second block dealt with the basic concept of blockchain technology and reported on its current state of the art. Thank you for your great contribution, and have a nice weekend, and see you next time.
Thank you, Professor. Any questions? Any questions from the participants? It seems no questions from the participants. No?
Thank you so much. I
Yes.
believe
Just we take a screenshot and then we will break for today.
Yeah.
I request all to turn on their video. Swati, Chinmay, Manloy, Srinivas, Sandeep. Okay, thank you, Professors Mingre, for the today's lectures.
Thank you so much. And then let me conclude this session with the following: you have a nice weekend, and please be prepared for the continuation next week, because we are just halfway through, and there are still plenty of thought-provoking things coming in the presentation. Thank you so much. Have a nice weekend.
Thank you.
So we will meet on Monday, basically. Professor?
Exactly. The same time and the same place.
Yeah, sure. Thank you. And participants, we will be meeting after 15 minutes at 4:30 for the late practices.
Thank you so much. Thank you, Vijay. See you soon. Bye-bye for now. Bye-bye.